about optimization. The thing about optimization is these are like your application problems that deal with derivatives. Okay? And so a couple of key things when you're dealing with optimization problems, again, these are usually when they want you to like maximize the area, minimize the cost, so on and so forth. So, first thing you want to do is you want to assign variables to given quantities and quantities to be determined. And if necessary, draw a sketch because that might actually help you figure out, you know, exactly what you're trying to find. Say you want to write an equation that is to be optimized. In other words, you're going to write an equation for the thing that you're trying to either maximize or the thing you're trying to minimize in terms of two variables. Third, you want to find the values that make sense to the problem. Okay, so find the values where the derivative of the equation is to be optimized equals 0. It's more than likely you're either trying to maximize or minimize something, which means you want to set the derivative equal to 0, and then basically solve for your variable. And you want to make sure that value makes sense. Lastly, you want to verify that you do indeed have a maximum using the test. Test meaning first or second derivative. And also remember, if you have any type of endpoints, you want to test those endpoints. So let's go ahead and just jump right into it, okay? So there's not much explanation after that for these types of problems. So the first one, we want to find the sum of one positive number and twice a second positive number. The sum of one positive number and twice a second positive number is 200. And we want to find two numbers so that their product is maximized. Okay, so what we're going to do is basically we need to do step 1. In step 1, set to go ahead and assign variables to the quantities to be determined. So we already know that we're looking for two numbers, okay? So we're going to make x represent the first positive number, and then y represent the second positive number. So I only have two variables here because I'm looking for two numbers. And then step 2 says to write an equation to be optimized. So I'm basically trying to figure out what the two numbers are so that their product is a maximum. So the equation that needs to be optimized is basically x times y, okay? Because when you multiply, that's the product, and I'm trying to figure out what the two numbers are so that the product is a maximum. P is just another random variable. You could have said A, you could have said Z, it doesn't really matter, okay? But I need an equation. And then step 3 says to find the values that are sensible or that basically make sense to this problem, okay? Well, take a look. It says the sum of one positive number and twice a second positive number is 200. Because the only way that we're going to be able to maximize this is if we have the same variable. Okay, so we can't differentiate with two different variables. So I have a second equation that says x plus 2y equals 200. Because it says, again, the sum of one positive number and twice the second positive number is 200. So I'm going to take this second equation and solve for one of my variables so that I can plug it in to the equation I'm trying to optimize so that I can take the derivative. So I'm going to go ahead, and it doesn't really matter. I'm just going to go ahead and solve for x. So that way I don't have to worry about dividing by anything and then possibly having a fraction. So now that x equals 200 minus 2y, I'm going to plug that back in to the equation I'm trying to optimize. So I have 200 minus 2y times y. So basically 200y minus 2y squared. This is the equation that I need to go ahead and optimize so that I can find my values. So I want to go ahead and I'm going to take the first derivative, which is going to be 200 minus 4y, and then I'm going to go ahead and set that equal to 0, because remember, where there's a max or a min is when the derivative equals 0. So I'm going to subtract over 200, divide by -4, and I get that y equals 50. Now I need to go ahead and test that that is indeed a maximum. So I'm going to go ahead and apply the first derivative test and test to make sure that 50 is indeed the value of y that's going to help me maximize my product between the two numbers. So I'm going to plug in a number that's less than 50, like 10. I'm not going to use 0 here, because I mean, I am dealing with two positive numbers, so I need a positive number. I could have gone 1, but I'm going to do 10. And I'm going to do 60. And I'm going to plug it into the derivative to see if indeed I get a positive on the left and a negative on the right. So I'm plugging 10, that's 200 minus 40, which is indeed a positive number. And when I'm plugging 60, that's 200 minus 240, which indeed is a negative number. So yes, I indeed have a maximum, and so y is 50, and that's going to help me figure out what the two numbers are. So y is 50 again, and then I can find x by plugging it in to the equation that I originally had solved for x. So that's going to be 200 minus 2 times 50. So 200 minus 100, which is, so those are my two values, 50 and 100, that are going to basically give me a maximum product. Let's look at the next example. A rectangular pen is partitioned into 2 sections and built from 400 feet of fencing, as shown in the figure. I guess the figure would help, right? So you got a rectangular pen and it's partitioned. Hopefully you guys know that partition means it's basically that it goes through the middle, or goes through it on the inside. And what dimensions should we use so that the area will be a maximum? Okay? So I need to figure out the dimensions here. So first thing, figure out my two variables, write equations, we optimize, and then find my values. Okay? Well, I know that basically I want to have x and y, length and width. Okay? So x is going to represent length, and y is going to represent width. Okay? I could have used L and W, but I already wrote down x and y, I don't feel like deleting. And so I need, so the area will be maximized. Well, we already know that the area of a rectangle is length times width, so x times y. And again, I'm put in the situation where I need to optimize my area equation, but I have two variables. So I need another equation. And I'm going to get that from that 400 feet of fencing. Okay? Fencing goes around, so we're looking at perimeter here. Okay? And so if I think about it, I have basically 3 y's. So I got to count the partition here because the partition is also made of fencing. So I basically have 3 y's here and 2 x's, if you look at it, because x refers to that entire length. So I basically have 2 x's plus 3 y's that should add up to equal my total amount of fencing. Because again, fencing is what's going to create this rectangular pen. I solved for one of my variables, and unfortunately here, yes, I am going to have a fraction. So I have x equals 200 minus 3 halves y, and I'm going to go ahead and plug that in so that I have my equation that I need to optimize, just like that last problem. So there's the equation that's going to be optimized. So basically I'm going to take the derivative of, so that way I can figure out what the dimensions should be so that the area will be maximized. So the derivative of my area is 200 minus 3y. So when you multiply 2 by 3 halves, you just get 3. Set that equal to 0 and solve. Divide by 3. And y is going to end up being 200 over 3. Okay? Now, I definitely need to test to make sure that that is indeed a maximum. So this time, instead of using the first derivative test, which don't get me wrong, there's nothing wrong with using the first derivative test. Okay? I'm going to use the second derivative test instead. Okay? So, and if you recall, the second derivative test is that basically when you take the second derivative, in this case it's going to be a -3, and then you actually plug in the value that you get, okay? Depending on whatever number that is, if it's less than 0, it's a maximum. If it's greater than 0, it's a minimum. If it's equal, then the test fails, and then you really have to use the first test. But the only thing is that when I plug in this value that I got here, 200 over 3, it's not like I can actually plug that in, okay? Because there's no like variable. So no matter what, it's always going to end up being negative 3. And negative 3 is less than 0, which means that we indeed have a maximum, a relative maximum. Okay? So this does confirm that this is the value that's going to help me figure out my dimensions so my area can be maximized. And then all I do is I plug in to, where's my equation? I'm going to plug into this equation to find x. Okay? So y equals 200 over 3, and x, when I plug it in, is going to end up being 200 minus 100. So my dimensions are 100 by 200 over 3. Last example that we're going to do, and then you guys are going to do some on your own, is we have a cylinder that's inscribed in a cone with a radius of 6 centimeters and a height of 10. And I forgot to attach the picture, so I'm going to do kind of a quick little mixture so you guys can see exactly what I'm talking about. Okay, can you see it? Can you see the cone? And the cylinder inside the cone? So you basically have this. So you know the height of the cone is 10. You know the radius is 6. And so you can kind of use that to help you a little bit when finding like the height of the cylinder, so on and so forth. Okay? So you kind of already know that because of this information, that this piece right here is going to be 10 minus h. You can consider this on the inside h. And then this will be r, the radius on the inside. Okay? So now back to the rest of the problem. Find expression for r. Okay? And technically, all this is basically given to you. This diagram here, this would be given to you so that way you can, answer these questions. Find expression for r, the radius of the cylinder, in terms of h. Okay? Well, if you take a look, you guys, we actually have similar triangles here. Okay? We have a similar triangle right up here at the top. Let me go ahead and let's label this. This is A. This is C. I really don't have that much space. I messed up on this, guys. I'm sorry. This is D. This is E. Go ahead and add this into your picture. Okay? So we have similar triangles here. Okay? So ABC and ADE, they're similar, which means that they're proportional to each other. So 10 over H over R equals 10 over 6. Okay? So again, ABC and ADE are similar to each other. So then that way I can actually use that to help me figure out an equation for my radius. There really wouldn't be no other way to figure that out. So that way you can get an expression for R. So I can cross multiply and then solve. And this reduces down to be 30 minus 3h over r. So there's your expression. Here's your answer to part A. Part B says find expression for volume of the cylinder in terms of h. Okay? Well, if you recall, the volume of the cylinder formula is pi r squared h. I don't remember if that is in your reference booklet, but you can always double check. And then what I can do from here is I can actually plug in the expression that I got for r. Okay? This is more of an IB problem. Like, it basically walks you through steps instead of actually flat out, what are the dimensions, like the other two problems do. It kind of breaks it into pieces, so then that way you can use a previous piece to help you answer the next part. And so you can leave it like this, or you can go ahead and multiply it through. I think that's what I'm gonna go ahead and do. I'm gonna go ahead and multiply it through. Remember when you square the top, square the top, square the bottom. Multiply through, and I simplify some. I can pull out a 9 at the top, so that's going to be a 9 pi over 25. On the inside, I'll have 100. I'm going to distribute the h through, and then minus 20h squared plus h cubed. There we go. All right. So again, the top, the numerator has a GCF of 9, so I can pull that out. That's where the 9 pi came from. And when I pull out a 9 from 900, I'm left with 100. A 9 from 180, I'm left with 20. And a 9 from that, and I get this. And of course, I distribute the h through. So there's my expression for volume. There's the answer to part B. Now part C says find dv over dh and find d squared v over dh squared. So basically the first and second derivative. Okay, I'm going to go ahead and change to the next page so that way I can have enough space. So my derivative okay? Don't do anything to the constant on the outside. You just take the derivative of the inside. So that's 100 minus 40h plus 3h squared. And then the second derivative of that, again, you do nothing to the outside. You just take the derivative of the inside. There's no product rule involved here because it's not like you have a completely new expression on the outside, okay? It's just a constant. So now I just have negative 40 plus 6h. All right. If you want to go that next step, you see there's a GCF of the 2. So then that way you can multiply that out, and you could also have 18 pi over 25, negative 20 plus 3h. You don't have to have this line here. You would have been just fine with that first line. So this is part C. And then part D says to hence find the radius and the height of the cylinder that will maximize the volume. Okay, so again, this is more like an IB problem because it walks you through each of the steps. Okay, and so you're going to set your derivative equal to 0. So that 9 pi over 25, 100 minus 40h plus 3h squared. Going to set that equal to 0. You're going to solve. What you should notice is that this inside part is actually factorable. If you notice, I haven't pulled out a calculator. No point in time, okay? This can't be done without a calculator. If I were to factor this, California method, that's going to be 300. I'm looking for two numbers that multiply to give me 300. Add together to give you a negative 40. So that's going to be a negative 10 and a negative 30. On top, you're going to put a 3h. And you're going to simplify, so you have basically a 3h minus 10 and an h minus 10. You're going to end up setting both of those factors equal to 0 to solve. So h equals 10 over 3, or h equals 10. And since you have two values here, you definitely want to test because, again, we're looking for the values that are going to maximize my volume. And so I have two values here, and I actually want to try to figure this out. So what I can do is I can actually use the second derivative test, which they probably want you to use, especially if they ask you to find the second derivative. Okay? And so if I do, and I do it with 10 over 3, so evaluate it, it's 10 over 3, and I plug in, see, 10 over 3 times 3 is just 10. Negative 20 minus 10 is a negative 10. So this is going to end up being a negative 180 pi over 25. Again, I plugged it into the more simplified form just to make the numbers a little easier for me. And what you'll notice that a negative number is less than 0, which means that you have a maximum at 10 over 3. If you were to do the same thing when h is 10 and plugged it in, you would end up getting a positive 180 over 25, which means that you would have a minimum at 10. But in this particular case, we're looking for a maximum. So our maximum value occurs when the height is 10 over 3 inches. So then to find your radius, you go back to that very first problem where you found an expression for the radius, and you're going to plug in. So 30 minus 3 times 10 over 3, which is just going to be 10 over 5. 20 over 5 is 4. So your radius is 4. Now, optimization problems, they do take some time, they do take some practice. So what you guys are about to do is you're about to do a few practice problems. Let me know if you have any questions.